I would like to invite Professor Stefano Liberati for giving the third talk today. So Professor Stefano Liberati is a full professor at CISA in Italy, and Professor Liberati has worked on various aspects of gravitational physics like analog gravity, emergent gravity, black hole physics. In particular, the review article by Professor Liberati on analog gravity is a first read for anyone who want to venture into these areas. So we'd like to listen from Professor Liberati further developments in these areas. So Professor Liberati, please start. It's all yours now.
Thank you. I wish to start today's talk with a few words regarding Paddy. I mean, it was, for me at least, it was a very important figure in developing my ideas. And I had the fortune to have several discussions with him and to know him, I would say, pretty well as a scientist, and also to have discussion about other things which were not just science. And I want to say just two things without being too rhetoric. One is that it's really, you know, there are many colleagues you meet in your life that from which you learn, but there are very few from which you learn how to think about problems. And Paddy, I think, was one of those people that was able to convey, in a certain sense, a vision, what a field could be and how to tackle some deep issues. And I think that everybody that interacted with him had the fortune to understand that. And the second point I want to make is that also personally, he was a very nice person, a person with which you can connect, a seeker of truth. And in a certain sense, I think he will be sorely missed also from this human aspect. So this is all I wanted to say, and but I think it is important in a day like today to remember these aspects of Paddy's personality. So what I'm going to discuss today, and I thanks the organizer for inviting me, is about analog models of gravity. Analog model of gravity, you know, have been a field of research now for more than 30 years. They are in a mature stage, but very rarely they are considered really toy models for emergent gravity. And I think that today I would like to try to convince you that this is the case. So let's start one step at a time. The first step is that clearly we have general relativity, and general relativity is a very nice theory, which nonetheless has some very tantalizing feature. Thermodynamical behavior popping out from purely gravitational objects, critical phenomena gravitational collapse. There seems to be a crisis at the level of cosmology. We still don't understand truly the content of the universe. And I would say that we not only don't understand dark energy, but I think there is growing energy and evidence that we still don't understand dark matter as well. And then there are all this strange behavior, the holographic behavior, IBS-CFT duality, the fact that you seem to require extra information in order to forbid causal paradox introduced by some solution of general relativity, the gravity fluid duality, this fact that you can rewrite the Einstein field equation as the thermodynamical equation, like Paddy showed very clearly, and the entropic force interpretation of gravity. And to me, the possibility to derive the Einstein equations and equation of state through a space-time thermodynamics approach that you may have just heard in the talk by Ted Jacobs. Let me just really spend a few minutes on this, because I think that there is a point that often is overlooked in this approach that goes clearly in the direction of emergent gravity, and that is the following. You know, the basic idea is very simple. You use the Einstein equivalence principle, you know that around any point of space-time you have a local flat patch, you can construct a Rocker-Rindel wedge, you can attribute to this wedge an Uru temperature, and at that point you can imagine that you perturb this wedge by a flux of some matter, and basically you look at the way you relax toward the point P, which is the bifurcation surface of your Rindel horizon. And what you find is that if you impose the Clausius relation where you identified basically the variation in the entropy as a variation in the area, basically resorting to the entanglement entropy and to the idea that basically the cutoff must be a constant if you imply also the strong equivalence principle. You say this is a gravitational cutoff and basically constant of gravitation should be universal. Then you put together the variation in the entropy as a variation in the area, and the variation of the area is basically a local variation in the expansion of the non-congruence, and then you can compute it through the Reichenau equation. On the other side, you have the variation of the flux, and that can be computed basically from the stress energy tensor. You put these together in the Clausius relation, and what you find, adding the conservation of the stress energy tensor, you basically find an equation, which is the Einstein equation, once you fix this cutoff to be directly related to H bar and G. Now, this is the things that everybody in the field has probably had at least once. But there is a point that I want to stress. This derivation, you see, relies basically on an ungranted assumption. Let me see what it is. You see, here you have the expansion and the shear. In order to arrive here, you need to neglect the expansion of the shear. The expansion, you are granted to put it to 0, because you see there is a term of order 0 in lambda, which is the fine parameter along the congruence. Here is everything of order lambda here. So basically what you need to have is that theta has to be 0, and but the shear doesn't need to be 0. And in fact, it was later on recognized in a series of work that it doesn't need to be 0. If the shear is not 0, you're in trouble because you don't recover the Einstein field equation. One way out is that you promote the Clausius relation to a near equilibrium thermodynamics. So you add an internal entropy production term. You see my pointer?
Yes, we can. Yeah.
Yeah. Okay. You see, you add an internal entropy production term, and you add. This is basically related to what is called normally an unmatched heat. So in normal thermodynamics, this would be the reversible level, and this would be the reversible level. And if you look at what is this term, it ends up being basically the analog of a shear viscosity. But this shear viscosity is exactly the Hartley-Hawking tidal heating, which is the work done on the horizon by the electric part of the vial, which is in turn related to the gravitational wave fluxes. So what is telling you this? It's telling you that when you excite this local horizon, part of the excitation goes in the deformation of the area, and that is basically reversible work. But there is another part that is going in irreversible work. It's telling you that this term, the Hartley-Hawking tidal heating, which is related directly to gravitational fluxes, should be seen as an irreversible, as a matched heat. But what it means that when I heat a surface, I create phonons, but I also create heat. But the difference is that the phonons are basically excitation on the surface. The heat is excitation of internal degrees of freedom. So what is telling you? It's telling you that this general construction is predicting that in a sense, what you call gravitational fluxes are directly related to excitation of internal degrees of freedom. They are in the space-time, they are not on the space-time. This is why they cannot be directly localized. Nonetheless, they transfer energy. So this is basically telling one point that I read basically one of Paddy's paper, which is if it can be heated, it has microstructure. So it is a strong hint that what we call the gravitational wave fluxes, basically are related to excitation of internal degrees of freedom of space-time. So that this, in a sense, has to be an emergent concept. And this doesn't require to say that quantum gravity models that we have are wrong, but basically that the way you should see these gravitational fluxes is related to the something happening to their internal structure once there is an excitation like this. Emergent gravity, of course, is a general framework. There isn't a theory of emergent gravity well defined. But of course, it's the general idea that basically you have a series of aspects that the metric has to be interpreted as a collective variable, that space-time can be seen as a condensate of more fundamental objects. The space-time symmetry may be emergent. Then singularity could be seen as phase transitions in the fundamental theory. And in a slight sense, all these pictures are, in a way or the other, now reflected in several scenarios that are embodying these ideas. Today, as I was saying, I would like to focus on analog gravity as as a really simple toy model. Of course, it's not the definitive one. It's just a toy model to learn what can happen in an emergent gravity scenario. So for those of you which are not so familiar with the analog gravity, let me basically introduce the basic concept. The topical example is that you take a fluid and you assume that this is really a perfect fluid in the sense that it's in V-sheet and is in rotational. By rotational, I mean that the velocity of the fluid can be written as the gradient of a scalar, which is called the velocity potential. What you can do is to perturb this fluid, and then you have two linearized equations, one from continuity and the other from Euler, but you can put them together, eliminating, for example, the perturbation in the density in favor to keep the perturbation in the velocity potential. And what you get a second order field equation, which can be described as a wave equation on a curved background. The background that you obtain is the so-called acoustic geometry, which is this form. Schwarzschild geometry, for example, in Pauli-Weierstrass coordinate can take this form, and a modulo a conformal factor. So this is a very useful geometry because albeit it cannot describe any solution of general relativity, it can describe all the healthy solutions, for example, Friedmann-Robertson-Walker, black holes, and so on. It can generalize this construction also to relativistic fluids. In that case, you get that the geometry, the acoustic geometry takes the form of a disformal geometry. Basically, it's eta mu, the geometry in the lab, plus nabla mu u and plus u mu u nu, where u is the force velocity of the relativistic fluid. These models of analog gravity clearly are not just acoustic ones. We have many models now that have been used and many experiments that have been advanced in this field. And basically, most of these models recur to the idea that you work in a regime where the analogy is almost exact, where basically you have relativistic waves moving on a curved background. But in a certain sense, what I want to focus on today is to go beyond, to say, well, but what happens if you really look at what is determined by the substructure below this emergent relativistic space-time? Of course, in order to do that and to be very interesting for us, it's better to have a system where there is a meaning to quantize whatever are these waves living on your emergent space-time. So one way to do that, a very popular analog gravity system, is the Bose-Einstein condensate. Bose-Einstein condensate, you all know what it is. It's basically a quantum system of an interacting boson, which most of them are in the same single particle quantum state. Basically, you deal in the non-relativistic case with a nonlinear Schrödinger equation. And what you normally do is do a main field approximation. Sometimes it's called the Bogolubov approximation. Basically, you replace your field operator for an expectation value on the ground state, the one that is overly populated, plus quantum excitations. And then you can even do another thing, because you can do an extra step and look basically at what this quantum excitation, reinterpret them as a collective excitation of the condensate, quasi-particle propagating on it. Let me see how you recover the analog model that we just saw in this case. Well, what you can do is that in this mean field approximation, you can basically substitute in the nonlinear Schrödinger equation the mean field. You will get an equation for the background with terms which are related basically to the back reaction of the quantum excitation, plus a term for the evolution of the quantum excitation. Now, one simple trick is that you can basically relate the quantum excitation to what you would call a hydrodynamic variable through the so-called quantum acoustic representation, but basically this would be the equivalent of the density associated to the excitation, and this would be the velocity potential associated to the excitation. And this is nothing else than a sort of Bogoliubov transformation, if you like. And then if you focus on this second equation, it can again be written as two equations, and these two equations basically can be united in a single equation describing the propagation if you neglect this term, which is called the quantum potential. You basically obtain, for example, for the analog of the perturbation in the velocity potential, you get again an equation describing propagation on a curved background on an acoustic geometry. This is not so surprising because basically in this limit you are describing the Bose-Einstein condensate as a superfluid with some excitation over it. But if you don't neglect that quantum potential, you can even go at next order. You see that the special relation that from this equation would be just the relativistic one. In this regime, you say you are dealing with phonons. In the full regime, you have a UV correction that is taking into account that your condensate is made of atoms, so your hydrodynamic approximation breaks down at ultra short wavelengths. And there is an additional term, which is a k to the fourth. Of course, if this dominates, imagine you neglect this, you get omega order p squared over 2m, which is exactly what you would expect for non-relativistic atoms. So this is a system where you can not only simulate the quantum filtering curve space-time, the relativistic one, but you can also have a model to simulate the UV physics, the UV completion of the theory. You don't have the Einstein field equation, of course, because the field equation determining the background is this first equation. We will get back to this soon. So let's see what lessons you can learn from this simple system. The first lesson I want to speak about is an historical one, and this has to do basically with the Transplanckian problem in black hole physics. So it's very clear that once you have an acoustic geometry, you can simulate basically an acoustic or a black hole. It's very intuitive. If you have, for example, a battery where the velocity becomes supersonic somewhere, it's clear that what is happening is that you will have a region from which sound waves cannot escape. And that would be equivalent to a trapped region in this analogy. So it was soon recognized that you can define a surface gravity for acoustic horizons. And in systems like BEC, you can even quantize these phonons. And so you have, in a certain sense, a way to describe acoustic Hawking radiation. And this was, of course, done. The standard Transplanckian problem concerning the fact that if you take Hawking quanta and you trace them back toward the horizon, they appear to be very largely blue shifted and in exponential way, in such a way that even before you reach the horizon, you reach Transplanckian regime, which seems incompatible with basically the quantum filtering curve space-time approach that is used in the computation of Hawking radiation. In particular, Bill Urru was very aware of this, and Ted Jacobson and Bill Urru were basically the main people working in the 90s on this problem. And sometimes, you know, people say, oh, you can boost away in high frequency, but of course, this is an S wave. You cannot boost away with an S wave, or you can characterize the problem by looking at scattering amplitude between incoming stuff and trace back Hawking quanta. You can rewrite that in a way that makes it clear that it cannot be removed so easily, this problem. And this problem was the main motivation, I dare to say, for the initial study in analog gravity. And what is the point? In analog gravity, exactly because you have that UV completion that we saw, which is a Lorentz breaking UV completion from the point of view of acoustic special relativity, you can see what is going to happen. You can see if the effect is robust against a given UV completion. And surprisingly enough, the effect is robust against the UV completion. What is happening is that you have to take into account the full dispersion relation. And in the case of the full dispersion relation, for example, if it is superluminal, when you trace back your rays, they will come from behind the horizon, from close to the singularity. And you could recompute the Hawking effect in this case. You will have in general 4 modes because there are 4 roots to this dispersion relation. 2 of them will be the relevant one for the Hawking effect. And the general lesson is what it is. The general lesson is, as long as the scale of Hawking radiation, which is fixed by the black hole surface gravity, is very well separated from the scale of Lorentz violation that here I call capital K. Parametrically, there is the scale which actually matters is parametrically related to the one of Lorentz violation. But basically, as long as this is the case, as long as still you have a well-defined Uru vacuum for observers which are falling with a preferred frame into the horizon, then Hawking radiation is robust. Basically carries on the standard way, you get the standard result. Of course, there are other nice features, like the horizon automatically becomes thick. You cannot appreciate basically the formation of the horizon below a given scale, which is basically the scale determining, the length scale determining this Lorentz violation, violating energy. But it's also, which, for example, automatically provides a cutoff for concepts like entanglement entropy. But the key point, what it is? The key point is that this fact, which theoretically was predicted and observationally, I would say since last year, I would say now is definitely visible in a lab experiment, then it's basically telling you that the Hawking radiation is robust against the UV physics. Although it looks like the black hole is a magnifier of UV physics, basically relates UV on scale minus to infrared to scale plus, the scale, if there is a separation of scale between the scale of Hawking radiation, which is the surface gravity, and the scale of the new physics, then you're safe. This is the first lesson, but there is another big paradox associated to black hole evaporation, which has to do with information loss. Now, probably all of you have heard very many times about this problem of information loss, but let me state it again. Information loss is a problem which is strongly related with this picture that you see on the right. Is the idea that you form a singularity and then you completely evaporate your black hole. The point is that if you take a pure state on sigma 1, there is no way you can describe a pure state on sigma 2. And the issue is that while in a surface like this one, you still have that the Hawking partner here can combine with the exterior Hawking quanta in such a way that on this surface, in a certain sense, is still defined a pure state, given that the operator linking the in vacuum to the out vacuum, the in vacuum here to the vacuum here is always a squeezing operator. This is no more true here, where you are obliged somehow to integrate out the Hawking partner, which are no more part of your space-time. This evolution, of course, seems to violate a unitary evolution in quantum mechanics, and it's an open issue now for many decades. A few years ago, I asked myself, what about analog gravity? Okay, in analog gravity, let's be clear about one point. There can be no unitarity violation. An acoustic black hole in analog gravity cannot remove the fact that this is a full quantum system, and if you don't kick out atoms from the system, this system is basically self-contained, and anything you can do on this system is not gonna violate quantum mechanics whatsoever. So the problem is, what is the point of view of analog gravity on this information loss? You see, the problem is that if I go in the analog gravity framework, of course, nothing forbids me to simulate a singularity. A singularity in analog gravity is nothing else than the region where the hydrodynamic approximation breaks down. There, you don't have a description of a space-time, of an emergent space-time. You have only a collection of fundamental objects, the atoms. So I can for sure generate a black hole, an acoustic black hole, which inside has a region which is not hydrodynamic. And then in a certain sense, if I let this object evaporate, how the unitary is going to be conserved. So in order to answer this question, it is clear that somehow, given that the singularity in this system is not described in the acoustic regime, you cannot rely on the mean field approximation there. So what we did was to resort to a different kind of picture. Another way to describe the condensation is to use basically correlators. So you can use the so-called Penrose-Osanger formalism, which is basically the idea that you look at two-point correlation function and describe and diagonalize them in an orthonormal basis of functions, which are called natural orbitals. These natural orbitals allows you to define basically ladder operators, and these ladder operators basically will define a number operator, and basically condensation, what it would be is that if you have an n total number of atoms, basically the condensate is there once n0. That means the atoms which are now in the condensate state, you can decide that n0 is the condensate state, is much larger than any other level occupation. So basically, if you have a perfect condensation, you will have a relation between this natural orbital, for example, for the condensate and the mean field. In general, this is not true, but this is a formalism that had the advantage to work perfectly also when you don't deal with coherent state, because in a sense, the mean field approximation is exact only when you are in a coherent state, but this cannot be a number conserving state, given that basically in general, a coherent state is a combination of states with different number of particles. What we demonstrated after that is that within this formalism, you can repeat all the standard machinery and derive basically the same equation that allows you to do analog gravity. Basically, you can recast the analog gravity in this natural orbital formalism. In addition, we did another step because we introduced ladder operators, which were a combination of the ladder operators associated to the natural orbitals, built explicitly in such a way that every time that you have a particle creation, you move atoms from the condensate to the excited part or vice versa. So we basically introduced a number conserving formalism. Why? Because we wanted to describe a situation where no atoms are leaving your emergent space-time. And of course, because if atoms leave the emergent space-time, then there is no point about the information. Some correlators will be lost because they will be gone with the atoms that you lose from your system. Now, once you have this machinery, in this conservation, number conserving formalism, you can try to do something which is basically akin to Hawking evaporation. We didn't do exactly Hawking evaporation because it's such an hard problem. So we did something which is a kind of proxy, which is the particle production in an expanding universe. So we had an expanding universe via basically, you can do this in Bose-Einstein condensate by controlling the scattering length, which is the nonlinear term in the nonlinear Schrödinger equation. That scattering length can be controlled in time with a technique which is called a Feshbach resonance. You basically apply a magnetic field and you change the scattering length. These introduce a time dependence in your acoustic geometry. And then by just controlling it, in principle, you can simulate, for example, Parker toy model of expanding particle creation in expanding universe. So we did so. And what you get is that the first things you learn is that in general, what is happening is that if you look at correlators, these are basically the Fourier transform of the phi1 field, which was the decomposition of the field in phi0 plus phi1 in the natural orbitals formalism. So the phi0 is the one depending on I0, and the phi1 are the one depending on any other higher order I. And what is happening is that if you look at this correlator, you will have an oscillating term in time, which is basically telling you that you take atoms out of the condensate, you put in the excitation and vice versa. But then you have two steady terms, and these steady terms are telling you that basically the correlation, this is lambda prime, is the final value of the scattering length that has increased. So basically, due to the expansion introduced by the variation of lambda, you have increased the depletion. So if you have taken atoms out of the condensate and put in the excited phase. But most of all, what you can do, you can say, okay, but what is the relation between the coefficient describing quasi-particle basically at late times than one at early times? As usual, they're related by a Bogoliubov transformation. But now you see these coefficients are involving not just quasi-particle on the condensate, they are really containing information about moving atoms in and out of the condensate as well. So this squeezing operator that you find, as you would expect to find, is a squeezing operator that operates on the whole Hilbert space, operates once you open this C coefficient, they operates on all the atoms in the condensate, those in the condensate phase and those in the excited phase. And the interesting point, so first of all, you have a unitary evolution on the whole Hilbert space. Secondly, if you look at the correlators between the condensate atoms and what you would call the quasi-particles propagating on the space-time, the analog in the black hole case to the Hawking quanta, you find that these correlators are non-zero. They are never non-zero at any time, and they are suppressed basically by the number of atoms involved in the particle creation, the number of atoms in the substratum involved in the region where the particle creation is happening. So from this point of view, the lessons that you find are quite striking because it's basically telling you, first of all, that there, of course, as we expected, there is no unitary violation, but the evolution has to be taken on the whole Hilbert space. Secondly, if you split your initial state in a stuff which is basically the mean field, whatever is in the condensate and for you is the space-time, times the quasi-particle a la standard analog gravity, then after you have particle creation, with this formula where you are able to follow the exchange of information between the substratum and the excitation, you find out that your state is going to be a mix. There's going to be correlation now between the atoms in the condensate and the quasi-particles. This correlation, of course, in a cosmology where this the whole space-time, where the particle creation is happening, will be suppressed by a very large number. But in a black hole, they will be suppressed by the number of atoms in the region where the particle production is happening, which will be a region around the horizon in the standard scenario. This region is becoming even smaller and smaller as you evaporate because the horizon is shrinking. So this correlation between the substratum and the excited quasi-particle are becoming less and less negligible. So what you have is that they are always present, but from a point on, maybe at each time, would be nice to understand, they become non-negligible and dominant, maybe in the late times of the evaporation. We have checked that, for example, back reaction works in this way, and this is exactly related to 1-0, if in a particular model of acoustic black hole, what is called a canonical, is a simple model of an acoustic black hole. Also, there is another interesting point. If you, at some point, when you have the squeezing operator you saw before, you decided to replace the operators describing the destruction or creation of atoms in the condensate by C number, basically, you go back to the mean field approximation, you lose those correlations that I told you about, but not only, you still get a squeezing operator, the evolution would be still unitary. And this the standard squeezing operator you find for particle creation in a quantum field theory in curved space-time. The problem, what it is that that evolution cannot be any more unitary once you arrive to the point, like in black hole, where there is a singularity, where you cannot have a full description of where the partner are. And then if you resort to the full description on the full Hilbert space, you still find everything is unitary, because simply you can describe that the Hawking partner are becoming of the part of the substratus. If you instead insist in the evolution with a squeezing operator, which is just acting on the Hilbert space of the particles, then you have to trace at that point on the Hawking partner, and information is lost. So the point of view emerging from analog gravity is that information loss is basically a semi-classical gravity artifact. Is as long as you work in semi-classical gravity, there is no way you're going to solve it, because you have to track the degrees of freedom of the substratum in order to be able to see that the evolution on the full Hilbert space is true. Of course, you can say, maybe quantum gravity doesn't work this way. The Hilbert space of particle doesn't speak with the Hilbert space of matter. They are completely separated. Personally, I find this point of view very counterintuitive for someone coming from gravitational theory, where what is matter and what is gravity can be changed with a change of representation of the fields, but of course it's possible. So the last lesson I want to speak about instead has to do with basically going for tackling another big issue. I told you about that one crisis brewing is the crisis concerning the non-obvious content of our universe. So the one interesting point is exactly if and how there is a cosmological constant in our universe. That would be the simplest explanation for dark energy. However, we all know that explaining with the vacuum energy the cosmological constant is very hard, because it's true that there is a vacuum energy associated to quantum mechanics, but we all know that this is basically divergent. And if you want to regularize it using the fact that the space-time is well-defined only up to the Planck scale, you get a huge number. So apparently, the interesting point is also in analog gravity, there is the same problem. Imagine you are a phononic observer living in an emergent space-time analog gravity. Your quasi-particle could be quantized, your phonons would have basically the same kind of Hamiltonian. And of course, when you are trying to compute the vacuum energy associated to your phonon, you get in the same trouble. Of course, you can say, oh, but there is a UV cutoff related basically to the Healy length, which was the one determining the capital kappa in the modified dispersion relation, and that will make the day. But that is still a very short time wavelength, and we would still produce a huge cosmological constant. So the question is, can we in emergent gravity really calculate the cosmological constant this way? What is a cosmological constant? What is the energy of the vacuum in analog gravity? So let's go back again to the the analog made based on Bose-Einstein condensate. You remember that we had the two equations from the mean field approximation, the equation for the quasi-particle and the equation for the background. The equation for the background, which I wrote here, is normally called the Gross-Pitayevsky equation. It would be this term and this term, because normally you neglected these two extra terms, which you remember, these were basically correlated of the quantum excitation. In one case, it was, I can remember, chi hat, chi Dagger hat, and the other one was chi hat. So these are called the anomalous mass and the anomalous density. Those are basically telling you that given the inequivalence of the vacuum of the atoms and the vacuum of the quasi-particles, basically there is always a bunch of atoms which cannot be in the condensate. This is the quantum depletion. So they back react on the system. But how do they back react? Can we cast this equation in a gravitational one? Now, if we can do so, for sure it must be a non-relativistic gravitational equation, something akin to the Poisson equation. But in order to describe the Poisson equation, you want to have matter which has a mass. So the first thing we have to do was, can we modify the theory in such a way to introduce a mass term for the phonons? And the things can be done because you can basically introduce a term like this one, which introduces soft U unbreaking, so that basically instead of a Goldstone boson, you have a pseudo Goldstone boson, which is endowed with a mass. Now, once you do that, you can ask yourself, can I identify the analog of the gravitational potential associated to my acoustic geometry? The answer is yes. You can recognize that your gravitational potential is encoded in the density perturbation. And if you adopt an ansatz where you basically take the flat space case plus a perturbation, then you can recognize that what appears in the Hamiltonian for the quasi-particles in the non-relativistic limit is exactly, if you look for a term that looks exactly like the term that you would have due to the action of the gravitational potential, you exactly identify the term, and this is what it is. Okay, now that we have identified the gravitational potential, what we can do, we can insert it back in the first equation and try to rewrite that as a Poisson equation. So we do two things. One is that we do this, what I just say. And then we basically consider a static background with a source term, and we imagine it as a localized distribution of quasi-particles, plus an unavoidable vacuum contribution, because you see this, even if you take home vacuum, the contribution of these two terms, the anomalous density and mass, is in general non-zero due to the depletion. So you will have a contribution due to the real phonons living on your space-time, and a contribution coming from the vacuum expectation values of these back reaction terms. This can be exactly cast as a modified Poisson equation. You have this extra term, which is telling you that this system is Lorentz breaking at a scale L, which is basically associated with the Hilly length. Then you have the standard matter term of the Poisson equation, plus a cosmological constant. And this cosmological constant is determined exactly by this depletion. And if you compute the energy density associated to this cosmological constant, and you compare it with the emergent energy density associated to the analog Planck density, because I call it this emergent, because you see, this G Newton is nothing else than a combination of microscopic parameters. Then what you get is that the ratio is a very small number, because this is of order 1, but this one, ρ0 times a cube, where A is the scattering length, is the typical length over which the atoms interact. This ρ0 a cube, in order for the whole condensation formula that I've used to be correct, has to be much, much less than 1. So this ratio is a small ratio. But you see, the interesting part is that the cosmological constant here is more directly related to the Hilly length, while the Planck scale is huge because it's related to emergent scale. In a certain sense, it's more fundamental, the cosmological constant, than the emergent Planck scale. And if you compute the cosmological constant explicitly, you find that it's really associated only to the back reaction of the depletion. There is this gas of atom. The condensate cannot be perfect. There is this gas of atom back reacting and basically giving you a standard back reaction on the background equation of motion, and it's a negative. So you naturally get a negative cosmological constant rather than a positive one, which is bad from the point of view of reproducing our universe situation, but it's good in a certain sense because it seems to favor systems which are closer to IDS. And in fact, you can reproduce IDS CFT system in analog gravity. But the point that we have to bring home what they are. What are the two main lessons? First, you see, the cosmological constant that we found has nothing to do with the 0-point energy for the emergent quantum field theory on the emergent spacetime. You see, you cannot compute, that is not a relevant energy simply because it's not the energy that appears to gravitate in the emergent analog of the gravitational equations. In fact, if it is this lambda is something that is totally non-perturbative and not derivable from the effective field theory of the quasi-particle and the condensate. It has to be computed at the fundamental level and is proportional to the quantum depletion of the condensate. So in emergent gravity scenario, implies that you can, if you want to say what gravitates, you have to derive basically your emergent Einstein equation. And only there you will see what is the analog of the cosmological constant. And again, the scale of the cosmological constant can be several orders of magnitude smaller than the energy scale that are typical energy scales in the emergent system. And this because there could be very small numbers, non-perturbative in origin, which cannot, again, be derived from the effective field theory framework. One note, you can redo the same reasoning for a relativistic Bose-Einstein condensate, and there, going in a corner of parameters where the speed of sound is equal to the speed of light, basically you remove to occur the Lorentz violation, and in that case, what you get from the equation for the background, you get Noston gravity. For those of you that are not familiar, Noston gravity is a scalar theory of gravity where all the metrics are conformally flat, and the conformal factor is the scalar. Bose equation can be recast in the so-called Einstein-Fokker form, which is the one you see in the box. And also in this case, we got a cosmological constant, in this case directly related to the lambda 5 to the 4th interaction that you have in relativistic BC. And this is a positive cosmological constant that would be renormalized by the contribution that instead we would find from the depletion that was basically all the source of the cosmological constant in the non-relativistic case. And here what gravitates is the trace of the stress energy tensor. You can show that it's the trace of the stress energy tensor of the fields propagating on the condensate. So you might say, well, this is all very interesting, but clearly what you found is a system which is not real gravity. You see, because at the end of the day, analog gravity is having a problem with background independence because you have a bunch of atoms living in a container, in a background space-time where things happen. So can we go beyond this? Can this idea about emergence can beyond? But first of all, there are quantum gravity models like group field theory, which are resorting to emergent Bose-Einstein-like ideas from a theory which doesn't have a background space-time to emerge a background space-time, a space-time structure. Secondly, there are observations like Marov's theorem that if you want emergent gravity Analogue model, it seems that you have to pay the price that the concept of what is local in the emergent theory should not be the same of what is local in the fundamental theory, which might be hinting to some form of non-locality required for a proper model to work. Background independence seems to be a key issue also if you go back, and I want to close with this, to the way we started, which was the derivation of the Einstein field equation a la Jacobson. Let me present you a small paradox. Imagine now, with all we have learned, I go back to the perfect fluid scheme. The very first toy model I presented, there was no Lorentz violation in the field because I was starting with a perfect fluid construction. And there I could find an acoustic geometry. This acoustic geometry is locally flat. And in such an acoustic geometry, I can construct a local Rindberg wedge. In such an acoustic geometry, I have a notion of quasi-particles. And if I can quantize them, I will have a very well not defined notion of overall temperature because everything is basically relativistic. Now let me use the Clausius equation again, and nothing stops me if I associate the Q to the photon energy flux to find again the Einstein field equation. So I had only to use entanglement entropy, but entanglement entropies, of course, can be defined for phonons, as can be defined for real particles on a space-time. So what did I do that was wrong? Because we know that the Einstein field equation are not the background equation. The background equation are continuity and Euler equation. So apparently the construction a la Jacobson brings you to a totally odd conclusion. And what is the conundrum? The conundrum is that even if you have worked with a perfect fluid where there is no Lorentz violation, no information about the UV behavior of the space-time and so on, like normally we do, you see, I made to gravitate the full stress energy tensor of the phonons. But that is not right. If you, as we have seen, for example, in the relativistic BC, what gravitates is not the full stress energy tensor. At most, it's the trace. The fact that it's the trace there was leading you to Nostrum gravity, which has background structure, as the causal structure of Minkowski, as fundamental rigid background structure. So you see, the key point here is similar. You have to be very careful in emergent gravity system to identify what gravitates. And this seems to point that if you will be able to find an emergent gravity system where what gravitates is the stress and the full stress energy tensor of emergent matter, then you will be able to recover Einstein equations. So in a certain sense, this is another very important lesson. It's very important that you don't give for granted what gravitates in emergent gravity, because it's basically strictly related to, otherwise you may put the answer in the question regarding the fact that if you're able to recover in some appropriate limit background independence. So in closing, we have learned 3 lessons today. So one is that Hawking radiation is robust in an emergent space-time, is UV robust, basically as long as you have a clear separation of scale. Second, the information loss problem in an analog gravity or emergent gravity picture, where you allow for the existence of a unique Hilbert space at the fundamental level from which both gravity and matter stem, basically the information loss problem is a semi-classical gravity artifact. It's an artifact due to the fact that you insist in separating a classical space-time and quantum fields over it. And this is not granted when you have to describe phenomena like the complete evaporation of a black hole. What you will get in this picture at the end is not a Minkowski with a thermal bath. It will be a highly correlated state between quantum gravity, fundamental constituents of space-time, the atoms of space-time, and the excitation making up apparently the thermal bath. There are a lot of correlation there between these two objects that would be able, if you have the full description of the Hilbert space, to recover the full information. Finally, in emergent gravity scenario, you cannot calculate the cosmological constant simply by using the 0-point modes of your quantum field theory. You have really to rederive your geometrodynamic equation. And only there you will see what actually gravitates. Many other issues, I think, are there, ready to be understood from this point of view. So I repeat, analog gravity is just a toy model of emergent gravity, but I think it has many lessons to teach us, and it could illuminate how, in the case in which space-time emerge from more complicated substructures, you should be able to think of the standing puzzles that we have nowadays in theoretical physics. So I think that I can finish with a famous sentence by Kepler that I cherish more than everything else of analogies. My most trustworthy master, they know all the secrets of nature, and they ought least to be neglected in geometry. And with this, I wish to thank you.
Yeah, thank you. Thank you very much, Professor Liberati, for such a nice talk on analog gravity. It's now open to questions. So any participants who have any questions, please unmute yourself and ask Professor Liberati.
Sumanto, I have a question. Can I ask?
Yeah, please go ahead.
Hi, Stefano.
Hi.
So, yeah, I agree with your point that, for instance, for the information loss, you have two Hilbert spaces which are sort of correlated, and one needs to account for a full back reaction. Have you seen any analysis done in the analog gravity in a full, the idea being, how do you couple, let's say, suppose I want to keep part of the system classical and part of the system quantum, and then have full self-consistent evolution of the system at hand?
Well, we tried, I was citing one of the last paper we did was exactly considering the back reaction of Hawking radiation in what is called a canonical acoustic black hole. And there we were trying to exactly see self-consistently in a number conserving formalism what is happening. It seems to corroborate the analysis we did for the particle creation, although we didn't do the particle creation. In that case, what you get is that the first step, so it's like, in back reaction, in principle, you have to iterate your process. Yeah. We did only the first step. The first step was in showing that the particle creation due to Hawking radiation was leading to a shrinking of the horizon, and that the relevant and the characterization of how much was the shrinking was related to the number of atoms in the region in where the acoustic black hole was, which was basically the N naught I showed in my previous slide. Yeah. So it's also corroborating the aspect that the correlators from between the atoms of space-time and the quasi-particle will be suppressed by 1 over N naught, which it means that they are always there, but they are going to be relevant only in the last phases of the evaporation. So we have a kind of first calculation that goes in the first direction. I don't know if I would call it a fully self-consistent description of the whole evaporation of such a black hole. Okay. Also, because there is an additional point that when you do it in a lab, I was talking before about the Stenauer experiment. In general, you don't have only an outer horizon, you also have an inner horizon. Such an inner horizon is in general, because you have a regular black hole, if you like, in that particular system. And in that system, the inner horizon is not completely stable. It evolves very rapidly, and it tries to push toward the outer horizon. So what I mean is that in the situation that you reproduce in the lab, you have even more complications because of this inner horizon.
Thanks so much.
Yeah, thanks. Supreet, there are two questions. I mean, two people have raised their hands. Sudipto, yeah, please go on.
Hi, Stefano. It was a wonderful talk. So I like to ask you two questions. I mean, first of all, in any of these analog gravity models, even starting with the Unruh's original idea, it seems there is hardly any role of the Einstein's equations. I mean, the equations for gravity. I mean, mostly it is modeling the metric and also the kinematical features of the metric. So how do one understand the actual Einstein's equation in the context of analog gravity?
Well, to me, the closer you can get is what you get in relativistic back. So in relativistic back, basically what you get is, what is it? Sorry. In relativistic back, you can show that if you look at the equation for the background, then what you get is exactly something that is very close to Einstein field equation, if you think, because it's Einstein-Fokker field equation. It's basically scalar gravity. This equation is 1913. 2 years later, Einstein arrived to the Einstein field equation. So the way you can get in an emergent system is basically you have to see what is the emergent geometry, and then put the emergent geometry back in the equation describing the degrees of freedom which are giving rise to this geometry. This background equation, in general, will lead to your analog of geometrodynamical equation. So far in acoustic in analog gravity, given that we always work with the realistic system, which are stuff in the lab, you cannot get rid of the background, the fact that these are not truly background independent. The best you can do is that you can left only with the background dependence on the causal structure of Minkowski, which is geometry in your lab. This is the closer you can get. And what I was saying the last part of my talk is that this doesn't imply that emergent gravity, a la analog gravity, with the idea, basically mutatis mutandis, the same idea, cannot work in absolute terms. There are these theorem Elamanovs that somehow you have to construct systems which have this different notion of locality at different, in the emergent scale and the fundamental scale. So from that point of view, I wouldn't say that it's obvious that it cannot work, but exactly the crucial point is how you emerge as well, the ground independence. I would say that that is the key point, which is tantamount to me to emerge a system where the stress energy tensor of the excitation gravitates.
So if I may ask another question, Shumanto?
Yeah, please.
So this is regarding this claim of the detection of the Hawking radiation in analog system. This Jeff Stanhofer and this group, the paper which came from Nature. I mean, that seems to be a clear validation of the analog models of black holes, the sonic black holes, if these are actually Hawking quanta they have detected. So I would like to know, what do you think about these experiments?
Well, the experiment, let me say, if you think, I mean, there were several iterations of the same experiment. Let's start with this. The experiment wasn't from the start flawless or totally convincing. The first claim was in 2015. The problem, which is very difficult, is to show that you have basically spontaneous Hawking radiation rather than amplification of excitation that are already there. You really want to prove that there is a particle creation from the vacuum. I would say that in the last iteration, the one published in 2021, there is a lot of work to show that this is fully consistent with a picture of particle creation in agreement with all the prediction of Hawking radiation. It is in agreement with the surface gravity that you would expect and everything. So I would say that for me, basically, the last iteration is settled the issues. The experiment, of course, is much more complicated. As you see, there are at least 4 regimes, and only one of them is the one in which you can say that there is Hawking radiation there is a clear signal of Hawking radiation. However, I would say that nowadays, most of the community agree that this is definitely evidence that the Hawking radiation can be reproduced in analog gravity. And I'm confident that with improving techniques, not only in Bose-Einstein condense, but for example, in optical fibers and so on, we will have a clearer and clearer result on this side.
Thanks a lot.
Yeah, thanks, Sudipta, and thanks, Stefano. There is another person who wants to ask a question. Charlie, would you like to unmute yourself and ask?
Yeah, okay, thank you. I just wanted to ask, near the end of your talk, you talked about the like an effective cosmological constant for the BEC system. What do you think the significance is, or is there any significance of the fact that it's negative, that is anti-de Sitter?
I think that if the mechanism, I mean, imagine now we go for some more general theory, something like proof field theory as a model that use condensation paradigm to emerge space-time, what they call geometrodynamics in place of the Big Bang. Then if it is depletion that is driving your cosmological constant, it seems very difficult to me that that would not be negative. But on the other side, if you have the relativistic BC system, then you can show that in the relativistic BC system, the lambda phi to the fourth, you have a kind of three-level term coming from the interaction of the relativistic interaction, which is providing you with a positive cosmological constant. So it seems to me that whatever in this kind of scenario, if you adopt this a condensation scenario from whatever is your quantum gravity theory to emerge your space-time and this geometrodynamics, then the answer will be a combination of the fundamental structure of the interactions of the constituents of your emergent space-time, plus the mechanism of depletion. And which of the two, what sign will prevail in the end, in a certain sense, may be a matter of model dependent there. But it may contribute to explain why you have a very small cosmological constant.
So it's like it just is very unlikely for them to exactly cancel. Like there will be some left over.
They have different origin. I would be very surprised if they would exactly cancel. There is no reason. I don't see a symmetry, or there isn't something like a supersymmetry, because they are living. If you like, they are at two different levels. One is directly related to the coupling constant of the atoms, lambda phi to the fourth in the nonlinear Schrödinger. Well, in the relativistic version of the, basically, when you do relativistic back, you start with a lambda phi to the fourth. And then you have another one, which is coming from the depletion. So it's a kind of byproduct of the condensation. So these two levels, there is no clear symmetry that tells you that they should cancel exactly. I would expect that they may work in opposite way, but I would be very surprised if they cancel, because I don't see some symmetry that should imply that.
I see. Thank you.
Yeah. Thank you, Charlie. And there is one final question from Kirill. Kirill, can you please unmute yourself and ask?
Yes, thanks a lot for this very interesting and very full talk. I have a question regarding the generalized second law. Is there any good underpinning of the generalized second law using analog gravity in either in the Newtonian approach that you have suggested, or any other one? And also, has there been any conceptual interpretation of the generalized second law based on the experimental evidence of Hawking radiation that made by Steinhauer and the other sources that you've cited?
This is a very good question. Basically, I don't know in the literature if I don't know of any study that has been dedicated to this, because in principle, you see, there is a kind of dogma that given that analog gravity doesn't reproduce the Einstein field equation, and given that the 4 laws of black hole thermodynamics somehow can be derived basic relativity theorems, then in a sense there is no hope to deal with that at the analog gravity level. Nonetheless, I would be more cautious to draw this conclusion, because just think about it. The first evidence, in a sense, that there should be a second law concerning the area came from the simple realization that if you have a super radiance, or if you like a Penrose mechanism, you can do it as long as the reducible mass of a curved black hole is not reduced. But the reducible mass is the square of the reducible mass is basically the area of the curved black hole. So in order to do something like a Penrose mechanism, you don't need the Einstein field equation. It is all encoded in the causal structure. So I don't know, it would be interesting to understand better how things may work.
Yes,
it's true that
to follow up on this. So so the irreducible mass is of an important concept to distinguish between reversible and irreversible transformation of the curved black hole, for example. And is there any? I mean, in analog gravity, one works with Bose-Einstein condensates. So what would be the irreducible mass of this Bose-Einstein condensate? Is there any good phenomenological view of this?
I don't know how to answer, because we are not able to simulate the Kerr geometry in analog gravity. In analog gravity, you see the Kerr geometry can be cast in a form which is basically the Kerr-Shield form, which is a metric plus the product of an half field. That is the Kerr-Shield form. Analog gravity, you deal with, even when you deal with relativistic fluid, the metric has always a Gordon form. That means it's eta mu nu plus u mu u nu, where u is a form velocity of the fluid, so it's a time-like vector. So one open issue is that we don't know how to simulate Kerr. I dedicated a paper to that with Matt Visser and a student of mine, and we basically showed that if you are slow rotating, or if your form velocity is almost null, then you can approximate Kerr very well. But basically, there is no known Gordon form of the Kerr geometry, and that would be very interesting also for numerical general relativity to have. So to make your question, however, to say something, Schwarzschild, the mass of the black hole is directly related to the velocity flow. The velocity, in order to reproduce Schwarzschild, has to go like square root of the mass over R. So basically GM over R, so if you really want to be picky. So basically, the mass goes like the square of the velocity times R. That is, I don't know if in Kerr you can say something similar. But definitely it's a very interesting question what you say, because it's not totally clear to me that you can get some kind of approximate laws of black hole thermodynamics in systems which are reproducing so closely, like in relativistic back, the field equation of Einstein.
Thanks a lot.
Thank you, Kirill, and thanks to Stefano. And,
can I ask something, Hemanta? Just one quick question.
Yes. Yeah, please.
So just thanks for a very nice talk. I just wanted to ask if there is a classification of analog spacetimes other than black holes, which
a classification
mimic gravitational
of analog what? Sorry,
analog spacetimes.
Yes.
Which mimic systems other than black holes, and that's what the question is.
A classification in a sort of a rigorous way?
No, not rigorous. I'm saying more examples.
Well, there are
beyond black holes.
People have played basically with black holes. There are several black hole geometry you can build.
Yeah.
They played with Freeman-Robertson-Walker spacetimes, hence including maximally symmetric spacetime like the sitter. They worked. You can simulate situations like. There are subtle ways in which you can even discuss ADS-CFT in analog gravity, and although less fundamental, you can even try to to discuss space-time with extra geometrical structure by introducing an external, for example, magnetic field. You can introduce another field, if you like. But
all of these with different kinds of velocity potentials, is that right?
Well, you have basically to introduce a different, basically space-time is characterized by the density, the velocity potential, and you have to satisfy, for example, in acoustic geometry, the Euler equation, so you will have to adopt some, maybe perverse external potential in order to reproduce that kind of metric. Of course, I stress, analog gravity is not only acoustic geometry. Analog gravity now is done in an optical fiber, refractive fluids, I mean, the gravity waves, if you are interested only in classical analysis. I mean, there is plenty of systems that now are under study in the analog gravity framework.
Okay, thank you. Thank you.
Okay, yeah, I think we can take one last question from Sudipto. Can you please go ahead?
Stefano, if I may ask you one question. So, as you have said that the velocity fields are related to the mass of the space-time. So, does it mean in this model the hydrostatic is basically the flat space-time? I mean, fluid at static configuration is a flat space.
Yes, if B equals 0 and rho is constant, which I think you get by continuity at that point, then you have basically Minkowski.
Okay. Thank you. Thanks a lot.
Yeah, thank you very much for such a nice and wonderful seminar and for agreeing to give a talk in this one-day conference. So thank you very much from the organizers, from the IAGRG, and all the participants.